Okay, thank you very much for the invitation. Very nice to be here. Sorry. I should figure out how I repackaged my notes. Yeah, I will write it. Okay. That's okay. It's in my notes, and my notes are here because I was reading them in 5 minutes ago. Yeah, I mean, since we are on TV, this is what people say, like, this is, you know, the beauty of being live on TV. You have this. Okay, sorry, it was a joke, but it didn't work. Anyway, where is it? Okay, I don't know. I'll try to do it by heart. Okay, so the title was, is here okay? Euler systems for conjugate-symplectic motives. Okay, so I apologize. Some of you have heard this talk before. There is a little bit that is new, but you know, not the majority. So I will immediately say that motives is just to have a shorter title than what I would have said if I had to use the thing that I will use, which is geometrical representations, which are an incarnation of motives that is easier to treat. So let me start with rho to be, so E is a number field. And rho is a p-adic representation of the absolute Galois group of E. And I will assume that it is geometric in the sense of Fontaine-Mazur. So this means that it is unramified at all but finitely many places, and the ram at p-adic places, which is conjecture, you know, Fontaine and Mazur conjecture that this comes from the Étale cohomology of some piece of some algebraic variety. So a motive. Okay, so this is a conference about the Bloch-Kato conjecture. So this is the Beilinson-Bloch-Kato conjecture. Okay, which says that the following are equivalent. So the first condition is that the order of vanishing at s equals 0 of L rho s is equal to R, okay, for any integer, so all integer R greater or equal to 0. I mean, I stated like this, but you could just say that this is equal to that. That will also be equal to R. And the second condition is that the dimension of the Bloch-Kato Selmer group of rho is R. So here, okay, this is a p-adic object, it's a complex object. So technically, you should just say that this is true for all or for one isomorphism between QP parents embedding. Okay, and if you like p-adical functions and your representation is appropriate at P, for example, ordinary, and maybe you want to avoid extra zeros, then here you could also take the p-adical function, and this would be the p-adic Beilinson-Bloch-Kato conjecture. Yes. No. Yeah, then I'm not assuming it, but I'm thinking it in my mind. So, yeah. Okay. So, thank you. All right. So there is some general ideology that I could call Hegnerism. Yeah, I said orally that, I mean, first I did not put P, and then I said that if rho is suitable at P, then you can consider the same conjecture with a p-adical function, and it's supposed to work. Okay, of course, you have to construct a p-adical function, and but also if you work in complex coefficients, then you have to construct the analytic continuation of the complex L function, so you have similar problems.
It's not complex L function, it's a p-adical.
Yeah, no, sorry. So let me rewind. So I said that this is a conjecture with complex L functions. But then now I say that I didn't want to write it twice. But so I just said orally that maybe in a different color. So if in orange, if rho is, I don't know, let's say Panchishkin ordinary, and I want to avoid trivial zeros, I will say crystalline. At places dividing P, then you can remove this embedding and just say that you consider a p-adical function, and the conjecture still makes sense. And it should be true. Okay, so there should be something linking these two terms. We don't really know how to do that, except in some cases when R is equal to 1. So the prototype is Hegner points on elliptic curves, and the ideology suggests that for some nice class of representations rho, one can define a notion, one can define special cycles or special classes, but they will come from algebraic cycles in some sense, in the Selmer group of rho, and add to the conjecture another condition that I will call 1.5. So condition 1.5 is that, when R equals 1. So what does it mean? It means that if I take R equal to 1 and then I use yet another color, so this would be for R equals 1. And this should be equivalent to, I'll write this also in red, but tell me if it's not readable, some special cycle or class is non-zero. Okay, so the typical example is rho is an elliptic curve, or the Tate module of an elliptic curve, and then special cycles are the Kummer classes of Hegner points. Okay, so they come from modular parameterization, and so in general, you expect these special cycles to be of some automorphic origin. I'll write here automorphic. And so I've said all the 3 words that I'm supposed to say for this conference. So what does it mean? What do you expect the nice class to be? So nice should happen when somehow there is some systematic reason to expect that you may have something in the Selmer group. And so if you look at the condition 1, then some systematic reason should be some systematic reason for the vanishing of this, which could be that there is a symmetric functional equation with root number plus or minus 1, I mean minus 1 in this case. And so this happens, for example, when you have some nice symmetry that forces this condition on the root number. And so the relevant case that you can consider is would be when rho is symplectic. or when rho is conjugate symplectic. So for conjugate symplectic, so this is a notion that appeared in Kobayashi's talk this morning. So this with respect to some conjugation. So you assume that E is some degree 2 extension of some other field, and then here you would have a conjugation, and conjugate symplectic means that you have a pairing, with a conjugate from the conjugate of rho tensor rho to QP bar. I took my coefficient in QP bar of 1, such that, okay, so you saw the condition this morning, so such that the induced representation is symplectic, induced from E to F. Okay, so I'll try to realize this ideology for a specific class of conjugate symplectic representation, which so some so this would be as follows. So assume that E is a CM field. So here F will be the total real subfield. And rho, again, some irreducible, well, I'll take it irreducible for later purposes. Conjugate symplectic presentation. This so rho from GLN of QP bar. Some reducible conjugate symplectic representation of dimension n. So here n, so unlike a symplectic representation, a conjugate symplectic one can be even or odd. So n is a dimension, I mean, of even or odd dimension. So n, for later purposes, I'll just write it as 2r plus alpha, where alpha is 0 or 1. And assume, so I have to, so I want to produce these special cycles, and for that I will assume some condition on the Hodge state weights of rho, so that for each embedding from E to CP, the Hodge state type of rho. So this contains this is a multiset of n weights, and I'll assume first of all that this multiset is regular, which just means it's a set of n distinct weights. And balanced. So I'll explain what this means. I'll go there, right? Okay, then in this case, I can construct some, I mean, I can make a notion of special cycle with this. Yes, I mean, I don't think it, I think I made it up, so yeah, I'm not assuming that anyone has it in their mind, but you know, hopefully the name makes sense. Okay, then I'll propose a definition of special cycles. So here balanced means the following. So you have these n weights, W. So I omit the tau. For each tau, you have these n weights. So there is W R. And here you have W R plus alpha plus 1. Okay, so this is R weights. These are also R weights. And then if n is odd, you have W n plus 1 over 2. So this is if n is odd. So the condition means that, okay, so what do you expect these weights to be on average? So the average of the Hodge state weights times 2 should be the motivic weight. And the motivic weight is, maybe if you take the average for tau and the conjugate of tau, the motivic weight, because of this thing, is 1/2 the motivic weight of the cyclotomic character, which is -2, so it's -1. So you expect, so the average of the W tau I would be -1/2. So this is a condition. And so balanced means that all these ones are, the first R ones are positive or equal to 0. And last R ones are less or equal to -1. And then, moreover, if n is odd, then you have a middle guy, and I want the middle guy to be either 0 or -1.
What is called the symmetry then? Independent of I.
Yeah, it's much weaker. I mean, it's weaker.
It is weaker.
Weaker, yes. Yeah. Okay, so I mean, I just make an example for which it's not weaker, but that people can keep in mind, which is that for n equals 2, you could take, for example, VP F. I mean, up to twist, and so some. So you could take where F is a modular form. This has appeared before, and chi is some anticyclotomic character. And then the balance condition here would be that the weight of chi is smaller than the weight of F. So this is a classical condition in the study of Heegner cycles. So somehow the point is that the anticyclotomic character can unbalance you, so you don't want to be too unbalanced. But I'll explain why. Okay, so here, so how one could go. So here is one way to find cycles. Okay, our Selmer classes. Okay, first of all, I said they are of automorphic origin, so you want to realize rho inside in some automorphic ways, inside the cohomology of some nice Shimura variety that you can work with. So there will be several pieces of data, but somehow it would be, I don't know, maybe the simplest thing you can do, but not simpler than that. So it will not be completely simple. So there will be some data. So you take some unitary Shimura variety, which is nice. So nice will mean that, so a Hermitian, so E over F Hermitian space of dimension n, and good signature. So here good means that the signature should be n-1, at one place, one infinite place, and n0 at all others. Then, so attached to it, you have some unitary group HV, which is the unitary group of V, and a Shimura variety, so which looks like some union of quotients of the unit ball of dimension n-1 in C, so it has dimension n-1. Okay, so you may want, and in fact it's possible if rho is automorphic, to realize rho. So suppose that you have some map, okay, there will be many in general, from the middle dimensional cohomology of xv over the algebraic closure to rho. And here you have to allow some coefficients. So I'll put here some automorphic vector bundle Lk, where K is some highest weight. I mean, some dominant weight. For H, and Lk is a corresponding automorphic vector bundle on xv. So you suppose you have a surjection like this for some k. This can happen for only one k. And sorry, here I want to twist by r. And then, yeah.
X bar.
X bar means xv base change to the algebraic closure of V. And this is I'll not write it in the following, but this is a Tal cohomology. So a Galois representation, and this should be Galois equivariant. R is 1/2 of n. I mean, the integer part of that. So n is 2r plus 0 or 1. Okay, so if you have that, then maybe to construct cycles, I mean classes in the Selmer group of rho, it's enough to construct classes over here. And so why should that be easier? So here we have f, which goes to, I'll do it on this side. So here you have the thing that you want. And so f gives a map from here to here from this group. And now this thing is a piece of the absolute Tal cohomology of, sorry, here I want to do, maybe let me do this, sorry. R is, yeah. I mean, when R is even, it's 2R, so I'll write it like this. It doesn't, yeah, I'll explain later why. So here, this is the absolute Tal cohomology of xv, its coefficients in the same thing. So this is not a sub, but if you, so there's a filtration, there's a Hochschild-Serre spectral sequence calculating this. And this is, if you divide by field 2 for the associated filtration, then this is a sub. And the quotient is just the geometric cohomology. So the cohomology on the algebraic closure. Okay, so how do I find an element here? Maybe I can find an element here whose class here is 0, and then it will give a class here. So why is this good? Because imagine that here you have just QP, then this receives, I mean, here you have classes of cycles of codimension R in X. So I would like a cycle of codimension R in X, and there are many because Schmorra variety is, is very symmetric, and so so this is here. So for a sub Hermitian space of good signature and codimension R, we get a unitary group HV prime and then a Shimura variety XV prime of codimension, which I can put inside XV, and this has codimension also R. Okay, so if R is trivial, if K is trivial, then over there you would get, I mean, okay, sorry for the people watching on TV. I'll use those two boards at the same time. So if R is trivial, then here you would have the class. So here you have a fundamental class. If K is trivial, sorry, here you have the fundamental class of xv prime, and then you just map it to via the inclusion to H2R of X. So it works and keeps us there. And then, okay, that's not enough. You need some kind of section here. So I'll assume I have a section. And in general, what do you need to do? So here, this fundamental class is always some element in H0 of X v prime with trivial coefficients. But you can push it here if you have some map that I will call F infinity. And maybe this F here, it would be upper infinity for some reasons that will be clearer later. So I can map this here if I have some F infinity, as I will write in that board over there. So and some F infinity in what do I want? I just want Hom from over HV prime from the trivial representation to trivial to this representation WK, okay, this algebraic representation WK, which is also the same thing as Hom from trivial chief, okay, for to LK. So then I can take the class of XV prime and then which has coefficients in QP of R, then I map it with coefficients in LK of R, and I get some class there. Okay, so I wrote a section, a Hecke equivalent. So the last piece of data I needed was a Hecke equivariant section S over there. So then if I trace all these things, then I will get some cycle that I will call Z of, okay, well, I will omit the S because it's less important, of V prime F infinity here. So this was what I wrote before. So F of JV prime. Maybe here I'll have the S. S JV prime of okay, so I have a class like this, and so definition. So here I'll assume n is even. The special cycle is a linear combination of those. Okay, so this, I don't know if you think this is simple or complicated, but I hope you think there's some margin to become more complicated because n was even. And when n is odd, it's a bit more complicated, and the reason is this. So if rho is irreducible of dimension n, then you do expect it to find in the middle cohomology of Shimura varieties, of unitary Shimura varieties of for Hermitian spaces of that size. But if you do this construction, okay, you can imagine you vary something, but the class of a cycle always lies in the even cohomology, even absolute cohomology, and then when you do this trick, you get some Abel-Jacobi class, which is in H1 of some odd degree cohomology. So somehow just doing this will not work for any codimension cycles when n is odd. But there is a correction, which is an idea of Yifeng Liu. Which is this. So if n is odd, so again, n is 2r plus 1 here. And here we'll assume it's at least 3. And if n is 1, then you already saw this morning what happens. Namely, you can do with Hagner points. Then what can you do? So you can construct cycles like this. So you get something over here. So now R, so you can do the same thing and you get cycles over here. But before you take the Kummer map, you add some twist to this. And the twist will be given by some CM abelian variety. And maybe to motivate this, maybe here is an example of some odd representation. So you could take sim 2 of VF, but now this is not, doesn't have the right motivic weight even. Tensor mu, where mu is like this morning, conjugate-symplectic of weight 1 or -1, I forgot. Okay, so you can imagine that maybe this will arise in a so this is a kind of a typical example in some sense. So this can arise in a Shimura variety, and this will arise in a CM abelian variety. So take a way to construct cycles is to construct classes is so you take mu, which is conjugate-symplectic of weight -1, and it's associated to a mu, which is a CM abelian variety over E. And now, so here, let's say of dimension d mu, and now if you look at H2 d mu -1 of a mu, with coefficients in here, then this contains mu viewed as a Galois character. And so a way to construct cycles is the following. So you have you consider the same cycles as before, but then you add another piece of data, which is this. So you take the Albanese variety of x, e, and then you imagine, but it will happen, that you have a map phi0 from Albanese to a mu. Sorry, phi0 will be the composition, and you compose it with the Albanese embedding. So you call this phi0. And now you take z of phi0, which is the graph. And if you look at its class, then it will be something of codimension d in xv times a, d mu. And now you take some cycle. The cycle you want to take is something as before, like z, v prime, f. But okay, this is a cycle in xv times a. Before I had a cycle in xv. So I just take my previous cycle and I put it back. If you take this cycle here and you cap it. A mu, yes, sorry. So you cap it with z of phi0. Okay, then you get a new cycle. And so its class will be in where? So h2r plus 2d mu of xv times a mu. But now if you, so this is the absolute, so this is the pullback of, so if you do the same game as before, so you take a section and then you want to take its Abel-Jacobi image, then you get this thing -1. So the degree will be this -1. So maybe I'll just write like this. So here. Yeah, from this Hochschild-Serre spectral sequence. So So I mean, yeah. So so somehow you have HP of E HQ of X bar goes to HP plus Q of X. And this is the associated. Okay, so why does this work? Because now, so we have a Jacobi class, this. So when I say Abel Jacobi, I mean you do this and you get something here. Will belong to H1 of E with coefficients in H2R plus 2D mu minus 1 of XP times A mu. I'll not write the coefficients now. But now here by Kuhnert decomposition, you will have H2R without minus 1 XP bar tensor H2D minus 1 of A mu. And so now here, yeah, so here before 2R minus 1 was just n minus 1, and now this is n minus 1. So, okay, so this works. Now here you have, yeah, so now you can imagine that here you have mu, and here you can have rho tensor mu inverse, and then together you get rho. And so the class here can be pushed via this phi to the Selmer group of rho. Okay. How am I doing on time, and are there questions? The time is there. Okay. Other questions? Okay. So of course, I mean, I can make any definition I want, but does it make sense? I mean, like, is it good for what we want? And what we want is the Benison-Bloch-Kato conjecture. So there is a preliminary question that you may have, which is, I had a list of remarks. I remember that there were 3, but I don't know what they were. Okay, so the first one is that you can do the same thing. For rho, which is symplectic for a total real field. But here it's always even, so you don't have to do this complication using as basic groups, orthogonal groups instead. And what I'm saying later is, I mean, yeah, some of the construction are also possible, but not all of them. Yeah, the second maybe here I should say that at least when K is trivial, this is proposed by Yifeng Liu. The second thing is that you want some class in H1F, so you would like to put an F here. Okay, so so if K is trivial, then all these Z's that I constructed belong to H1F of E rho by a theorem of Nekovar and Isiol. So because they come from algebraic cycles. And in general, somehow periodic geometry doesn't move fast these days, so you don't know. I mean, sorry, this was also a joke. Periodic geometry moves very fast, but somehow I don't have a reference in the literature which says somehow that this also makes, yeah, that can be directly applied. But let me tell you what you could do. And I'll assume for the rest of the talk that they belong to H1F. It's possible that something like that can be extracted from the literature. So one thing is K. K is the weight here. So something from which you construct some automorphic. Sorry?
K equals 0 means constant
K, yeah, so K is a weight in the sense of representation theory, so it means trivial representation, so trivial local system, so yes, constant coefficient. Yeah. So here, so in that case, you just have plain algebraic cycles, and by Nekovar and Iziol, you have something in H1F, and their proof goes by comparing with symptomic cohomology, and so maybe you want to get some construction like this, where here you have some symptomic, I mean, you don't have to know what this means, symptomic analog of these sheaves, and hoped that what they do applies. And so there is some recent work by Imai, Kato, and Usis, which does construct these things on Shimura varieties of hyperspecial level at P. And then, okay, so I don't know very well these things. So probably, I mean, it's possible that then you can have a comparison between some symptomic regulator and natal regulator also for this situation by also some recent work by Guo and Reinecke, but I'm not so sure. So I'll put a question mark here and hopefully I'll have something more precise soon. And another option is you may want something better than symptomic. You may want something like arising from the analog of a Kuyasato variety. So if you have a modular curve, then these sheaves can be a piece of the relative symmetric powers of the universal elliptic curve called the Kuyasato variety. And then this means that your cycles are actually sort of, you have some big cycle in some big variety, and then you have pushed it and cut it in some ways to get a cycle on the base Shimura variety with some coefficients. So this works, yeah, I'll just write names without writing what I'm saying here. So if XV were P of PL type, so modulus space of abelian variety, then by theorem of Ancona, you also have, you even have some motivic version, so relative motive here, and then you could probably even imagine applying directly the result of Nekovar and Iziol, but this is not PL type, it's abelian type. So constructing this seems very hard. But then you could also, what you could do is take some variant of these abelian varieties that are of PL type. You have to take some kind of similitude unitary groups, and it's also possible, but a bit less natural. Okay, so I'll just leave with this discussion. So for the rest, I'll assume that these cycles are in H1F, and assuming that here are the main theorems. Okay, so theorem, maybe I'll put some quotation marks, first of all, because I have to finish resolving that thing, and also have to finish writing the paper, and also I use another paper that people have to finish writing. So the main theorem is this. So if rho is as above, so conjugate-symplectic of regular balanced weight, and some more conditions. So F is not Q. So this implies that these varieties have, these Shimura varieties are compact. So that's helpful. And I want to assume a conjecture that I'll state later. It's called mod. So it's the modularity of certain generating series. And rho has big image. So I'll not specify what this means, but it's not too bad of a condition. Then, so 1.5 implies 2. So some special cycle in that sense above is non-trivial. So some special cycle is non-zero, implies H1F of E rho is one dimensional. And then to complete the picture, well, okay, you would want at least that 1 implies this, some non-vanishing coefficient. I mean, you want to know that in some cases this condition is satisfied, some non-vanishing criterion for these special cycles. And this we proved in some joint work with If and Liu, but I'll just say, okay, so the consequence of our work combined with this in some special case, which is more concrete, which is this. Sorry? I don't have a sign condition, but if you, yeah, okay, so you can assume that epsilon of rho is -1, but if that doesn't hold, then every special cycle is 0. Okay, so here is some theorem. So suppose that A over F is an elliptic, a non-Siam modular elliptic curve. Okay, and then there are some conditions that, first of all, I don't have time to write, and okay, so mild conditions, local conditions. For example, that A should be semi-stable and good reduction at P. Or maybe I'll write this, good ordinary reduction at P. All places dividing P plus some other mild conditions. Then there is a criterion in terms of the p-adical function. And sorry, but I have to tell you for which representation. So for rho sim n, so n here will be, yeah, so 2r minus 1 of vp a and any r positive. So in general, what we do is that we prove some non-vanishing criterion for these special cycles in terms of p-adical function when the Hodge state weight is the same as the Hodge state weight of this, so the simplest possible, and under some conditions. And n is even. Okay, so how do you prove this thing? You actually construct a special cycle which is more special than others, and then you construct an Euler system on top of it. So the proof construct some very special cycle theta 0 in H1F of E rho plus some Euler system theta m with base class theta 0, and then the machinery of Euler system implies the theorem. So which machinery? So there is a version by Yetchev, Nekovar, and Skinner of the machinery of Euler system that is adapted to what I want to do. So I'll explain how to do this in the time I have. So as remarks, maybe I should also say that there are some related works. So the first one is by Graham and Shah. So they prove, well, you can deduce the same result, for fewer rows. So for example, what they need is that n is, well, basically these rows come from base change from a symplectic representation. So n is even, and also the weights have this symmetric condition that you mentioned. And it's also based by a JNS Euler system but based on a different class, on some different class. And then for other similar work in high dimension, if you take rho to be the product of two representation which are conjugate set of 12 dimension n and n plus 1, then there is work by Liu, Tian, Chow, Zhang, and Zhu, and also which they and also by Lai and Skinner. So they constructed, so they use GGP cycles. They constructed a JNS order system that's somehow easy, and you will see from the proof, hopefully, that this is easier. And here they construct a bipartite order system, which is another variant that is harder. And maybe I think Shilin Lai will try to explain this thing and maybe try to prove that it's not only easy, but it's trivial to construct these systems if you read his paper, but I'm speaking before him, so I'm not worried. And the third thing is that, these only work for conjugate symplectic motives, and these work also in the symplectic case. And so in the symplectic case, you can't have your life too easy, but for n equals 4, and in symplectic case, Naomi Sweeting has constructed a bipartite Euler system based on some class which I would call theta cycle, which is constructed in the same way as the one I'll present. Okay, and of course you have to do another thing, which is prove that, so before you, okay, so this will give you that if theta 0 is not 0, then H1, the Selmer group is one-dimensional, and then you have to prove that somehow, if you have some other special cycle which is non-zero, I mean that these classes somehow generate all special cycles, and this is some representation theory which I don't have time to explain. So maybe I'll explain the construction theta 0 and then of the other system. So remember, here I'll take n even. So remember that we started from some map. We wanted some map like so. But actually, what are these maps? So this is known or almost known. So the paper, I don't know, I think the paper has not appeared. Like Yixin, Xin, and Zhu to be somehow spanned by representations of certain automorphic representation of HV of the adels, namely the ones such that whose Galois representation is associated, whose Galois parameter is rho. So there's finitely many of those. So this means that I mean, if I put some level here, then I will take the level, I mean, corresponding part over there. So my assumption is that you have something like this. So you can imagine that your non-trivial thing comes from some f here, which is in some infinite part of one specific one. So I'll fix this specific one. And maybe, yeah, so then I also, so the theta is for the theta correspondence, so I'll fix some, the standard additive character. And attached to this sigma, you have the theta lift of sigma, which is, so what is it? So it's a representation of some other unitary group, but of split signature, RR. So the quasi-split unitary group. You'll see why it is useful. So this is a holomorphic discrete series. Same size. Same size, yes. Yes. Is it 5 minutes. Okay, good. Okay, so this is characterized as follows. So by the non-vanishing, so we have this thing such that if you look at a certain space of trilinear form, it's not 0. So the coinvariant space of this is not 0. So HV here. So this is a representation of G of A. It's a representation of HV of A, and this thing here that I'll explain is a representation of both. And what is that representation? It's a wave representation. So on R copies of your vector space. So HV is clear how it acts. And G, it's the okay, so let me call this lambda. So in fact, it's known that it is a line. So when it's not 0. All right, so you have arranged to have such a thing. So now I want to construct this theta, which will depend on 3 parameters. How do you do this? So construction of theta. Okay, so I do it in 3 steps. So the first step is that I take f infinity as above, and f small lower infinity in form from 1 to this representation wk. And then for each x in v to the r with you have to do something a bit more general than that, but it doesn't matter. So with you look at the Hermitian form, and you construct some R by R matrix, and you want this to be positive definite. Then if that is so, then you can construct v prime of x, which is just this orthogonal to the span of x. And then you get a cycle, which is z of f x f. This is just what I called before, maybe z of v prime of x, f infinity. So why do you put f and f together? Maybe somehow you should think of some avatar of sigma where you replace this by the finite dimensional representation wk. Okay, so yeah, so like avatars, this is like there could be half man, half animal. So this is half smooth and half algebraic, but it works. And then you can do the same thing for pi and omega. And that's sort of the right framework, but I don't have time. But anyway, you have these cycles, but you have many of those, and I want some canonical element there. Some canonical theta 0. So how do I do that? So the second part is that for phi in omega, which is this space of Schwarz functions, but also, okay, all right, maybe phi infinity is some polynomial times q to the t of x. I'll just retain this polynomial, and q is some exponential. I construct something called theta d of p and f, which is the sum of z of x q to the t of x weighted by t of x. And the conjecture mod is that this is, so these elements are in, this is a formal Q expansion with coefficients in the Selmer group. So the conjecture is that this belongs to H1F of E rho, but it's a Q expansion of some modular form. So, so these are modular forms of weight K for the group G. So I'll take another couple of minutes, if I can, to finish the construction. So I will assume the conjecture. Then in that case, so inside here you also have pi, the theta lift of sigma. And the third part of the construction is that for P in pi dual, then I can construct theta of P, so var phi, P, and F to be theta of what I had before, paired with phi. Okay, this is the pi pairing. And now, so this eliminates this part, and so this is just some cycle. Okay, so I took many choices, but somehow you can see that this is equivariant for the action of G and H, and so it factors through this line lambda, and so it's kind of canonical. And then you have to construct some Euler system on top of it. And so I'll just say one word, I mean, one sentence. So what is an Euler system? You will take in this sense, I mean, in the sense of J and S, you have some tower of ring class fields and then some compatible system of classes which satisfy some compatibility condition. And the way to construct things in tower is that simply instead of taking these cycles here, which came from xb prime, so you just take some connected components of this, which is so how this goes by the determinant to xu of 1, but this is so in the limit, it's something like this. So if you take a connected component, then somehow connected components can be related to the parameters for, I mean, by class field theory to the parameters for ring class fields. And this gives so somehow elements of the Selmer group for over ring class fields. And then you have to choose your parameters f, phi, and phi to be suitable so that you have the right conditions of JNS, and it's possible. That's it. Thank you. Sorry for going over time. I think so. This result, I think it's only known for compact Shimura varieties. So this implies that this is not this is compact. Okay, and if n is 2 or 3, then I mean, if n is 2, sorry, then it's also okay because it's a modular curve in the non-compact case, so you know how to get around. But in principle, somehow the architecture works in the same way. No, for these representations, it's constructed by Aishan, Harris, Lee, and Skinner. And we reconstructed in our case with Yifeng just for what we needed. Also, I should say that in the result with Yifeng, there is no conjecture mod in the result, not because I forgot, but somehow we prove it based on our assumption. I mean, yeah, we proved it in our case, so that result is. There you're in the ordinary case, and for the other system you don't need any assumption at P. Yeah, but maybe I should say that if you are in the Panchishkin ordinary case, then you get you can extend this in the anticyclotomic power.